Hello and welcome to the webcast titled Securing Military Data at the Edge. My name is John McHale, Editorial Director with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. Our speaker today is John Mellot, fellow chief engineer for secure processing at Mercury Systems. This event is sponsored by Mercury and hosted by Military Embedded Systems Online and Open Systems Media. Before we get started, I have some housekeeping items. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. The webcast will consume about 40 to 45 minutes, leaving the remaining time for the Q&A session. Now let's take a look around your viewing console. You'll find on the right-hand side an area where you can enter questions in real time. We'll encourage you to ask questions throughout the session while that question is still fresh in your mind, and we'll address as many as we can during the closing Q&A portion. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the webcast. And please note, as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the webcast with more information. Now, on the other side of the panel, you have the left-hand side, there's a resources section, and that's where you can find today's slides and speaker information. Two more features we're excited about here. Your console is customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, and presenters for your ideal viewing experience. Just expand them to get a closer look or close them to have the presentation window automatically resize around them. For maximum screen size, close them all or use the full screen mode control in the upper right-hand corner of the presentation window. To bring them back, simply click on the buttons in the bottom middle dock. In an effort to make these webcasts more accessible, we've added closed captioning in nearly a dozen languages. To enable this functionality, simply click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. This webcast will be archived online at the same URL you used to join today's live session and be available within 48 hours. And once up, it'll be available for at least 1 year. Now I'm going to turn it over to John, who is an excellent speaker. I've been with him in live events, and you will learn a lot. John, take it away.
Thank you, John. Appreciate it. Thank you, everybody, for joining our presentation this morning. You can see the abstract for this. Edge computing in the military domain is of particular interest since most systems are edge-based, not cloud as we find in commercial cases. It's really important that software and hardware in these systems securely process and disseminate information. So we're going to talk a little bit about some of the requirements and best practices for encryption and security using commercial technology in this presentation. So the agenda for today, we're going to talk a little bit about what is the edge and how that's evolving, requirements, the role of cryptography in particular at the edge, as that is one of the key solutions for security, and then talk about some of the solutions that Mercury offers for security at the edge. So first, look at really current platforms and in the past. In case you're wondering, what does edge computing really mean? It's anything that's really co-located with the user. In all cases, whether they're military or commercial, you co-locate compute with the user for reasons of performance, latency, and factors like that in order to enable those systems to perform well. It simply isn't feasible to do everything in cloud or even that intermediate between edge and cloud, the fog, so-called fog computing. It needs to be right there with the user, and because military edge computing is right there on the battlefield, physical security is actually a really key attribute for these solutions compared to perhaps some things in the commercial space. And some of the key characteristics historically have been that non-platform resources have been isolated. So you might have a mission computer, for example, in a platform that doesn't necessarily talk to outside resources beyond the platform itself. Or if it does, on very limited linkages to well-known endpoints, as opposed to something that's say network connected potentially can be communicating with many different things. There are a lot of parallels in the military computing at the edge use cases to what we've seen in the operational technology, industrial control systems in the commercial domain. If you think about things like factories and power plants, electrical distribution controls, historically those things have been isolated, and over time connectivity's been added. As we've evolved. And speaking of which, as we look to the future, the addition of high performance networks that are connected, not just between individual endpoints, but between multiple disparate platforms and multiple domains of operation, is going to become the new norm. And this connectivity also includes legacy systems that will be retrofitted with connectivity for those applications, allowing, for example, satellite intelligence to be widely disseminated among different users on sea and air. Land users maybe being able to call on support from maritime assets and so forth. Because of the networking, this produces greater opportunities for adversaries to exploit those systems as these systems become really dependent upon those communications for their full functionality and delivering their full capabilities. They start to look more and more like things that we've seen in the OT and ICS domains that you've seen in the press, for example. And I'll point to things like the Colonial Pipeline incident, where ransomware actors were, able to do things that resulted in that pipeline being shut down and having significant impacts on energy delivery in the eastern U.S. Threat actors have operationalized these over-the-network attacks not previously possible because the network interfaces didn't exist. So this has to be a key consideration as you contemplate developing security for military systems at the edge. So we're going to move on to talking a little bit about requirements for military computing at the edge. And really a lot of these ideas, again, also exist in the commercial space. Starting with probably the one that's cited the most in the U.S. for DoD systems, DoD 5200.39, which calls for identification and protection of important, what's called critical program information in military systems. With respect to edge computing, among the most important of these include anti-tamper, that is the ability to deter, deny, detect, and respond to actual hands-on tampering with the device. Not all U.S. military systems, in fact, most are only used by U.S. operators. They are often designed for exportability. There are foreign military sales. No doubt you've seen F-35 and other major systems that are exported. These are, obviously marquee platforms, but there are numerous other devices and capabilities that are exported to our partners in order to enable them to have capability parity with the U.S. forces, and allowing greater interoperability between the U.S. and its allies. With the additional connectivity and the leveraging of more capable operating environments and military edge computing, such as I've seen in commercial systems, cybersecurity is also, again, becomes a very important consideration, not just when the platform is initially deployed, but over its entire lifetime. Information security and physical security are also additional considerations that are very relevant. Each platform and system is different and will generally have varying requirements. depending upon risks and consequences and the realities of operating that system. So there's no one-size-fits-all solution. You can't just buy, a box or a widget and say this is a secure computer or a secure storage device, whatever, and say this meets all of my requirements. But there are a lot of common themes, right? And so these components I just mentioned can provide valuable building blocks with which to realize complex systems that deliver system security at a higher level. One of the other requirement sets that is beginning to impact military edge computing is the risk management framework. This is a relatively newer concepts developed by NIST that is really talks about the entire life cycle of computing systems from inception to grave, and how to build it correctly and continue to operate it securely over its lifetime. The three big foundations of this, and what failure to adequately protect the system may lead to loss of confidentiality, integrity, and/or availability of the system. So the risk management framework is really about protecting that confidentiality, integrity, and availability. If you're exposed to this, you'll see that there is a process for developing each individual system. It has to be tailored based on the risks and consequences, and provides a solution for better protecting the confidentiality, integrity, and availability of systems. One of the punchlines of this is that, again, as I previously mentioned, you shouldn't expect that you're going to be able to deploy a system that has a significant compute component and walk away from it for 20 years without having to provide updates and maintenance of the security of the system. Today, there are expectations that cyber requirements will be addressed with ongoing updates over the life of the program, and so this is an important consideration as you plan for and implement a military edge computing system. So I want to talk a little bit more about confidentiality, integrity, and availability. These are really the principles of information security, and they each mean different things. So confidentiality is really about restricting information, so it's only accessed by authorized individuals or functions, and especially in embedded compute systems. When we talk about authorized entities, functions may be that rather than people, and prevention of unauthorized access to data. Not all data requires confidentiality, but some data does require confidentiality, and it's important that those assets in particular protected. Whereas integrity is really about the accuracy and consistency of information, and that it remains unmodified and trustworthy throughout the life of the system. This is actually really important, because if you don't have integrity in your system, if you start it up and run it and operate it without integrity, then you really don't know what the system is doing, and you then can't make assurances of confidentiality and availability. So it's intimately linked to all these three founding principles of InfoSec are. And availability is actually also a key part of this. When we think of availability, we often think of things like redundant power supplies and system level redundancies, which are absolutely important and critical. But again, if you have breakdowns in integrity and confidentiality in your system, those can ultimately impact availability, and leading to denial of service, for example. Talking a little bit more about the importance of these factors in confidentiality, what is information there and why is that important? That information in an embedded system, an edge system, may be software or firmware, or it may be other data like things like AI weights or coefficients that are used for an AI system. It may be parameters that determine how a system operates in the field. Revealing that information may give an adversary an advantage that allows them to develop counters or to make copies of the capability, reducing the advantage to the warfighter who uses the system. When we talk about modification information, it's important. So what happens if you have a breakdown of integrity? You can change function or produce misinformation that results in ultimately changes in what happens in the future. So if you can, for example, through integrity, make it so that a system doesn't recognize a threat, then that means that the ability of that system to counter that threat goes away. So that's another very important characteristic. And then, we talked about availability on the last slide, so I won't dwell on this there, but I think everyone will agree that availability is a necessary attribute of military edge compute systems. So in this next section, we're going to talk a little bit about the role of cryptography at the edge, and this is a particular focus area of this presentation. First, cryptographic protection. Why is it important? We talked about at least two of the foundations of InfoSec: confidentiality and integrity. Cryptography is a very important tool for maintaining both of those things. Military systems often have, because they're edge systems and not necessarily have great connections to the outside world, often host on each individual unit a software, firmware, and data that needs to be protected from disclosure to the adversaries. What encryption provides for you is a means to protect a very large secret. Whatever that information is, you have to protect with a very small secret, cryptographic key. And the punchline here is that if I have a very small secret, it's easier for a system implementation to conceal it and protect it than you can with a large secret. I mean, for example, if you consider a hard drive full of terabytes of information that might have been collected from a sensor, and it might be something you want to maintain as a secret. It's very difficult for all that data to be stored in a way that protects its confidentiality without the use of cryptography. So with cryptography, a relatively small function that can be heavily protected can protect the key and protect the operation of the encryption function, so that data is better protected. And with respect to integrity, there are a couple of mechanisms that are particularly notable for where cryptography provides benefits. First is the use of hashes, which provide means to measure information of nearly arbitrary size, providing a digest value, kind of like a fingerprint, such that if there's a modification anywhere in that information, it's highly unlikely that you get that same fingerprint or digest back. And that's illustrated in the picture on the right, which may be a little challenging to read, but the point of this is that if I have a piece of information that if as an adversary I want to make a small modification to, it's very hard for me to do that without causing that digest change, which provides a means for detection. Digital signatures are another means for verifying the integrity of data, and can also be used to attest integrity to other parties. Digital signatures leverage public key cryptography, and the advantage of that is that, unlike just a hash by itself, where knowing the hash at either end is an important thing, but that might be vulnerable to potentially other people learning that information and exploiting that. Digital signatures provide a means that doesn't depend on a secret key for somebody at a remote location to verify that the value is what it's supposed to be. So, for example, if you consider a BIOS image in a computer, for example, that'll typically be signed by using secret key in a trusted location, and the system, when it boots up and then it reads that BIOS and can verify that signature to assure that the BIOS is actually what it's supposed to be. So some of the uses for cryptography in military systems at the edge include protecting the confidentiality and integrity of data at rest. And this can be in a couple of different forms. One is hardware-based storage encryption. And if you think about self-encrypting drives, which I'm sure everybody has seen, those are a great example of such a solution. Those are not the only solution available, but certainly that's one of them. Another approach is to use software-based file system encryption and authentication. This may provide some advantages over hardware-based storage in that authentication can readily be incorporated into that solution, and where it may not be in a commercial hardware-based solution. Not to say that that doesn't have value, but that can be a second layer and provide advantages. And in fact, if you look at things like commercial solutions for classified processing and data storage, those are actually aligned around multiple layers of protection realized with commercial solutions in order to achieve something that can be approved at a classified level. So you may have actually, in some of these cases, call for both types of solutions in order to achieve the security you want to achieve. Another use case that I just mentioned a few minutes ago was protecting software and firmware stored in non-volatile memories like BIOSes or FPGA bit streams that are storing those MBMs directly on the hardware and used during secure boot. Integrity is actually often more important than confidentiality here, because if you can't assure integrity, then how you boot up and hand off to an operating environment that is going to run your application is actually you've lost everything at that point, because you can't assure the integrity of the system, so you don't know what's going to happen there. Measurement of and attestation of the configuration within systems is also another very important capability that cryptography can provide. That measurement may be measurement of different components within a circuit card assembly, all the way up to measurement and attestation across multiple FRU or LRU units within a larger system. So that's another key capability that cryptography can provide. And last but not least, I'm going to highlight here, and there are certainly other use cases, is cryptographic sanitization. It's easier to make small secrets to go away, both in terms of the effort and time, than to zeroize a large secret. And again, you can point to that hard drive example. Erasing that whole hard drive could take minutes, if not hours. Whereas if I can zeroize the key used to decrypt that hard drive, then I've denied the ability for somebody to go recover that data. So the takeaway is cryptography is an important tool for securing military systems at the edge, and it's also one of the more cost-effective ones, because it covers a large number of different considerations with things that are relatively easier to implement and maintain. So compared to hardware solutions that attempt to do these things through physical means. So the next thing I want to talk a little bit about are what kind of cryptographic standards you have to take into consideration in military systems at the edge. So the National Security Agency defines a suite of algorithms that are approved for use, and were referred to as national security systems. This suite, that CNSA 1.0 suite, it's referred to as now as the 1.0 suite, formerly just CNSA suite, lists a number of algorithms. The advanced encryption standard is a symmetric key algorithm used for encryption and decryption of data. Elliptic curve Diffie-Hellman is used for key exchange between parties. That's generally used in concert with the elliptic curve digital signature algorithm, which is used to authenticate those sorts of transactions, as well as I previously mentioned, to verify the integrity of data from others. The secure hash algorithm, as I previously mentioned, this allows fingerprints to be taken of data. This is actually an integral subcomponent used to generate and verify digital signatures. And for example, if you want to sign a BIOS, for example, a hash is performed on that BIOS, and that hash is in fact what's signed by but with the signing key in the digital signature algorithm. Older algorithms, the reverse Shamir-Alderman or RSA algorithms are still applicable in use, and at 3072-bit key size or larger. One of the big advantages that RSA provides, and why it's still an important algorithm today, is that for a signature verification operation, it's very fast. For systems that have a very demanding, say, boot time requirement, an RSA algorithm solution may be preferable over one based on the ECDSA solution in order to help meet those requirements. This was last revised in 2015, taking into account future transition to quantum computer-resistant algorithms. You may have heard about these in quantum computers in the press recently. It's believed that some algorithms, such as ECDSA, will be vulnerable in the future to quantum computers that have not yet been developed. Predicting technology breakthroughs and evolution can be very challenging. In the case of military systems, national security systems, they typically have a very long lifetime, and the data they're protecting often has a very long amount of time that you care about that data. Whereas something like a bank transaction, once it's completed, that may be the total lifetime of that importance of that information. So this transition, and we'll talk a little bit more about this on the next slide, would be expected to take many years to occur, and should be complete long before a potential threat can be realized. So the CNSA 2.0 suite was announced in 2024, and it identifies a suite of quantum-resistant algorithms that are approved for national security system use. All the algorithms that listed here are believed to be resistant to attacks by quantum computers, again, which haven't been developed yet, so no practical attack has been realized. So this leverages, in particular, recently approved NIST post-quantum algorithms for digital signatures and key establishment. So MLChem and MLDSA in particular are the two replacements for ECDSA and EC Diffie-Hellman. You'll note that AES is still part of the suite, and AES 256-bit keys is believed to be resistant to anticipated quantum computer attacks. And the secure hash algorithm is referred to really as SHA-2, and the 384 and 512-bit variants is also continues to be approved for general purpose use in quantum resistant systems. There's a statement by the NSA that the expectation is by January 27, new acquisitions that start at that point must be planned to be CNSA 2.0 compliant. And the expectation is the phase out of the CNSA 1.0 suite will be concluded by 2035. So obviously a decade is a long time, but for these kinds of systems, those kinds of lifetimes are not unusual compared to, say, commercial implementations that may turn over much more quickly. It's worth saying that anytime there's a cryptographic transition, one of your key considerations has to be interoperability. So you may have requirements to employ quantum resistant or post-quantum algorithms in your implementation, but you also may need to interoperate with legacy systems. So you may have to support both of those capabilities. Next thing I want to talk about are side channel attacks in cryptography. Side channel attacks are fairly well known at this point. Talked about in public literature for a quarter century now. They are enabled by unintended information leaks from the implementation of the cryptographic algorithm. This is not at all related to the threat of quantum computing with some algorithms. This is completely an independent consideration. Side channel attacks are generally performed to recover the secret key from a system. So that might be an encryption key that's used to encrypt and decrypt data, or it might be a key that's used to sign data. The kinds of paths for leakage are manifold, but typically the ones that most people are concerned about include power dissipation that can be measured outside of a device, electromagnetic radiation that can be potentially be measured without even coming into physical contact with the device, or timing variances in a system's operation that may be observable by an adversary. Generally speaking, SCAs in many cases are going to require hands-on interaction with the system. Assets at the edge are this is a particular consideration for them, since an asset that's lost in the field, for example, may be something upon which side channel attacks can be performed by an adversary. I will say that for network connecting devices, as timing variances in the system and crypto operations can wind up resulting in timing variances and the response of a system over the network, and in some cases that may be something that's exploitable as well. And that's another reason why timing is an important factor in side channel attacks by adversaries. What do we do about side channel attacks? Well, first we employ countermeasures. So ultimately, all side channel attacks rely on the observation correlation of information that's leaked and the secret information, right? So it's not just merely enough to observe power emanations often enough. You typically need to see that secret information flying by so that you can correlate these things. So in some cases, if you can observe a single cryptographic operation using implementation that's leaky, it could leak the entire key in that one operation. And things like ECDSA and RSA are examples where such leaks may exist. You can just literally, say by hooking up an oscilloscope to the power on a system under attack, observe that. And some of the early papers by some of the founders of cryptography research and the late 1990s, 2000 timeframe actually literally demonstrated that against payment cards. So that they were able with just a single operation, just literally to read back the key from observing the power emanations from the device. In other cases, an attacker has to observe many operations in order to recover a key. So you can consider an algorithm like AES, which uses a secret key. Generally, you're not going to be able to look at the power or the EM emanations and recover that key in a single operation. It may take you many observations in order to recover that key. But one thing we do know is that every implementation leaks to some extent, no matter how good its countermeasures are. And those without countermeasures leak generally badly to the point where even using a single key for a few hundred blocks of data may allow an attacker to recover that key. So what do we do about this? There are really two main classes of countermeasures we like to talk about. And the first that we talk about is leakage reduction countermeasures, which effectively reduce that signal to noise ratio of whatever the adversary is observing. And typically in electronic systems, that's going to be EM or power. And that falls into a couple of different techniques. One is simply to reduce the leakage signal. So that signal of interest, if it can be identified in the circuit structure, it may be possible to implement features in the circuit that actually reduce that emanation, that signal. And the second approach is to remove that correlation between the secret and the emanations. That effectively increases the noise. And a great example of that are techniques that split the secret key with random data that effectively removes that emanation and performs operations that can be later recombined to produce the answer, again, without revealing that key. This will enforce the observed increase the number of operations necessary to recover a key. In case of Mercury's own implementations, they've demonstrated that solutions that don't have countermeasures, literally leak keys in maybe even hundreds of operations, whereas implementing leakage reduction countermeasures can increase that to orders of magnitude higher. Millions, tens of millions, even hundreds of millions of operations have to be observed successfully in order to recover a key. So what this means is the effective lifetime of a key can be extended. So this leads to the next approach is the implementation of protocol countermeasures. These reduce the exposure of a key by changing it frequently. Techniques include most commonly referred to as key rolling, where a key is updated by a known mechanism between two parties, so that exposure of the key, of any single key, is reduced to a threshold below which an attack is not possible against any single key. This essentially prevents an observer from observing enough operations to recover that key. The best protection, obviously, the conclusion is combine both leakage reduction and protocol countermeasures. And if you appropriately guard band these things, these can provide you a lot of assurance that your countermeasures are adequate. The one thing to know is that countermeasures and attacks are involved in science. And while we can have an understanding of what our countermeasures do today against existing attacks, the field of research is an active one, and future attacks will no doubt be more powerful. There will be new techniques that are always being published in the academic community, for example. And so this is something where you need to make a risk-based assessment of how to guard band your implementation enough to provide you the assurances you want for the future. And I'll leave you with one more thing here. Implementing effective countermeasures, especially leakage reduction countermeasures, is extremely difficult. And while many people can theorize a countermeasure for a particular purpose, actually getting it to work successfully and provide that benefit is a non-trivial exercise. And in our own development of countermeasures, we've actually attempted to implement many different countermeasures developed and published in academia and other open source literature, and found many of them provide little or no benefit, or even in some cases make things worse, not better. So, I will leave it at that on this. So I wanted to continue to talk a little bit about some of the Mercury solutions for security data at the edge. First, I want to talk a little bit about Starlab, which was recently acquired by Mercury Systems just a couple of weeks ago. They're a longtime partner of ours. Many of our customers have been working both with us and with Starlab. So we're really excited to bring them on board and find ways to create solutions that provide additional value to our mutual customers. Starlab's Titanium Protection Suite is a capability that works with common Linux distributions. So things like Red Hat, Red Hawk, and so forth, are all things that Titanium can work with. And these are actually very important in many military computer systems that use high performance compute based on Intel processing. Starlab goes a long way to addressing RMF security control requirements. It provides support capabilities like eliminating and deprivileging users, which reduces attack surface in the system. Implements mandatory access controls, and includes features such as encrypted file systems, as previously discussed. The Titanium Secure Boot feature also prevents malicious modification of system boot. Again, enhancing that system integrity, so the system you boot is the system you intended to boot. The Titanium's Technology Protection Suite is not specific to Mercury hardware, and in fact can be employed in virtually anybody's hardware that runs a Linux distribution. The next thing I want to talk about are some of Mercury's built secure, rugged, trusted servers and their related OpenVPX SOSA line processing boards. And the OpenVPX secure processing solutions, we have up to data center class processing with Intel Xeon processors in a 6U VPX form factor. This is a ruggedized solution suitable for the most harsh environments. And, the ability to provide Xeon processing in this form factor is a unique to Mercury capability. Additionally, these are protected with Mercury suite of built secure IP to provide the level of trust and assurance you need for solutions that require security. We also have similar capabilities in our rack mount secure processing solutions. These are data center class processors, again, with dual Intel Xeon processors, large amounts of storage, memory, high-speed I/O, many expansion slots. This is implemented with a trusted rugged motherboard manufactured by Mercury in the US, designed in the US, and also protected with built secure IP. Mercury is a leading supplier of semiconductor IP, that is designs for FPGA and ASIC circuits. These cryptographic solutions are available with Mercury's market-leading side channel attack countermeasures, and are trusted by industry leaders such as AMD, which uses them in its Versal family, and Microchip, which uses them in its PolarFire family. And those devices are shipping today. So that is, an example. And there are many others who also trust Mercury to deliver these solutions tailored for their particular use cases. Some of Mercury's solutions in cryptographic IP include its SecRun suite, which is a comprehensive suite of SCA-resistant cryptographic algorithms, which also includes its KeyGuard key management hardware function. This is an important feature that adds to cybersecurity by eliminating the need for the host operating environment to handle key material. This can be wholly held within KeyGuard, which distributes key material to cryptographic functions through private interface, preventing any adversary that might be in the operating environment from getting access to those keys. SecBoot is an enhancement of SecRun that provides a means to securely initialize memories, random access memories in a system from non-volatile memory. The typical use case for this is boot. However, it can be used at runtime to load any block of data that requires confidentiality and integrity checks with an autonomous function that does not require software to actually perform these operations. Encipher is an important anti-tamper solution that provides transparent encryption authentication of DDR memory as protection of DDR memory at runtime. This can be realized in devices like Xilinx's MP-SOC, where you can, in the hard processor subsystem, run an operating environment like Xilinx's Linux or another operating environment from third party. And this can transparently encrypt the DDR memory that's connected to this as operating environment operates out of. Encipher includes both leakage reduction and protocol countermeasures for side channel attack resistance. So this is really a comprehensive capability that does not cause a functional change in the operating environment for protecting that data that needs to be stored in that large bulk memory. And then finally, I highlight Phantom Black, which is Mercury's physically unclonable function. This provides a unique fingerprint to semiconductor devices used as an identifier for authentication purposes or as a component to contribute information to protecting a key store. And a great example of that might be a key that's provided to KeyGuard functionality in order to protect other keys that are stored in non-volatile memory. And then the last hardware solution I want to talk about here is Mercury's NSA Type 1 encryption solution for data at rest. This is a drive encryptor for protecting secret and below data. Again, Type 1 certified, and it's designed for harsh environments such as aircraft and unmanned platforms. And then finally, we've shown you a lot of different pieces here, things that Mercury can provide. Typically, you don't just buy a single widget to realize a security solution, but you bring together many pieces to realize that security solution. Mercury has a cadre of system security engineering personnel who can work with you from the initial design of your system all the way through getting to deployment to tailor that solutions to enable your success. This is incredibly important since every system, every use case has different requirements. And bringing those together and making the program successful and on time and realizing those capabilities is absolutely critical. And so Mercury doesn't just give you a component and documentation and throw it over the fence and you're stuck figuring it out for yourself. With these services, this really enables you to be successful. And with that, I'd like to hand it back to John McHale. Thank you.
Thank you, John. Excellent presentation, just as I predicted. Good job. Now let's get to those questions from the audience. Question, side channel attack countermeasures are an important feature in cryptographic implementations. As a consumer of these implementations, though, how do I evaluate the efficacy of these countermeasures?
Yeah, that's an incredibly challenging problem right now. In the commercial space, there are starting to be some standards as to how that's done. In recent years, Cryptography Research Division of Rambus, along with partners, has developed commercial assessment techniques that are based on essentially a level of effort intended to provide some assurance that that countermeasures aren't trivially bypassed. But it doesn't necessarily provide the level of insurance that you look for in a defense system where that lifetime or the consequences of compromise are much larger. So in these cases, you have to look for additional artifacts that can provide you some assurance of that. First and foremost, the vendor should be able to explain how it's tested it itself. And provide information on that and its quality of the results from that, and then you need to look maybe at the provenance, who else is using it in similar applications, and how they got through the hoops of understanding that it meets the requirements adequately for the solution.
Okay, next question. Do I need security engineering services? Shouldn't secure products be usable with vendor documentation?
So, strictly speaking, you could buy a product, get the documentation, and figure it out yourself. Inevitably, that extends the amount of time that it takes to realize your solution, and dramatically increases the risk that you will miss something important. And this is true of not just security solutions, but other complex systems. That level of support is very important for customer success. And as I stated, Mercury has this cadre of system security engineers who can help your program be successful with its products.
Question here from the audience. I see data at rest and data in motion, but what about data in use?
Yeah, absolutely. That is a key consideration because data in use is, actually, that is where all the pieces come together and are sitting there exposed. The Encipher solution I just talked about is a great example of a product that's intended to address that. You're also starting to see the integration of cryptographic protection for external memories and things like Intel processors. So Intel's total memory encryption feature, for example, is an example of a similar capability. Compared to Encipher, which incorporates effective side channel attack countermeasures, these commercial solutions are intended to address a different threat scenario. Typically a commercial data center environment that doesn't necessarily have the same considerations. So you have to keep that in mind, that it's not equal. Not to say that it isn't valueless. That it's valueless. It is valuable. And also the other thing to consider is it's not available in all products at this point. So as you look at these options, you have to make trade-offs if you feel that such a solution is necessary for your system.
Okay, time for one more question here. Do all Mercury security products require Mercury hardware?
No, absolutely not. As we highlighted before with Starlab software, we have third parties that are not using Mercury hardware that license and use Starlab software, and we will continue to offer that. And then our semiconductor IP, like our cryptographic IP, that is widely used by third parties in their own hardware solutions. And so, we plan to aim these Xilinx with their Versal chip as being one of those, microchip with SpolarFire FPGA being another. But we also have numerous customers across the DIB who also are successfully using Mercury semiconductor IP in their own FPGA or ASIC implementations.
Okay, that brings us to our time limit for today. Sorry we cannot get to all your questions. Someone may get back to you after the event with more information. I want to thank John for speaking today and Mercury for sponsoring this webcast. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used during today's live session, as well as the URL shown on your screen, and be available for at least 1 year. Look forward to seeing you on future Open Systems Media webcasts. Goodbye and have a great day.
Thank you.
Thank you, John.